In this lecture, we talk about holomorphic structures on surfaces. A Riemann surface is a smooth surface with a holomorphic atlas. This means that our surface is covered by open sets, U sub I, and for each I, there's a diffeomorphism, call it phi I, from Ui to an open subset of the complex plane, in such a way that on the overlap of two open sets, Ui and Uj, the transition function from one chart to the other is a holomorphic map from an open subset of the complex plane to another open subset of the complex plane. An orientation-preserving diffeomorphism between open subsets of the complex plane is holomorphic even only if it's conformal, meaning angle-preserving. That means infinitesimally on the tangent space it takes infinitesimal round circles at one point to infinitesimal round circles at another. This is a notion that makes sense on any Riemannian manifold. So if S is a smooth orientable surface, we can choose a Riemannian metric on S and then ask whether we can find open subsets in the neighborhood of each point and a diffeomorphism from that subset U to a subset phi of U in the complex plane, which is conformal as a map from the Riemannian metric on S to the Riemannian metric on the complex plane. Supposing we can do this for each point, then the collection of these conformal maps produces a holomorphic atlas on the surface S, compatible with the conformal structure coming from the metric. In particular, this would give a method to prove that every smooth surface admits the structure of a Riemann surface. In fact, we can always find such conformal local charts. Let's explain how. Let's try to characterize what it means to say that a map from a Riemannian structure on a surface S to the complex plane is conformal. Let's let U be an open subset of S and phi be a map from U to the complex plane. When is it conformal? Well, let's write phi as f plus I times g, where f and g are real valued functions on S. To say that phi is conformal means that the Hodge star of df is equal to dg. If we apply star d to star df, the result is the Laplacian of f. On the other hand, this is equal to star d dg, and d squared of g is 0, so consequently the Laplacian of f is 0, which is to say that f is harmonic. We can reverse this order of deduction. Supposing we can find a function f which is harmonic on our surface S for the Riemannian metric near a point P, and let's suppose that the differential of f at P is non-zero. Since it's harmonic, star df is closed, and therefore locally we can find a function g so that star df is equal to dg. Then taking phi to be equal to f plus I times g defines a local conformal chart. So we've reduced the problem of finding a conformal chart to the problem of constructing a harmonic function. There are several techniques to do this. They all involve some analysis, and we will not give details. We've indicated the proof that every orientable smooth surface S admits the structure of a Riemann surface. This is a local theorem. It guarantees the existence of holomorphic coordinates locally on the surface, and it raises the question of when one can find a single coordinate single coordinate giving the structure of a Riemann surface which works everywhere on the surface simultaneously. This is typically impossible when the surface is not simply connected. The uniformization theorem is a theorem, therefore, about the universal cover of a Riemann surface S. It says that the universal cover of every Riemann surface is holomorphic to exactly one of three Riemann surfaces: the Riemann sphere CP1, the complex plane C, or the open unit disk D. Let's indicate the proof of the uniformization theorem. There are many details that we're going to suppress, but we want to give the basic idea. How would we find a uniformizing map? Let's suppose our universal cover S twiddle is holomorphic to the open unit disk, so that there's a holomorphic isomorphism phi from S twiddle to D. And let's suppose it takes some prescribed point P to the point 0. How would we find the map phi? Let's define a function f to be minus log of the absolute value of phi. This is a function which is harmonic and non-negative on the complement of the point P, and with a singularity of a prescribed type at the point P. What we're going to do is to try to construct the function f directly by the Perron method. It's hard to directly construct a harmonic function on a Riemann surface. What's easier is to construct a function which is subharmonic. Let U be a domain in the complex plane. A real-valued function f on U is said to be subharmonic if the value at each point is less than or equal to the average on a small round ball centered at that point. The class of subharmonic functions on a domain U is closed under the following two operations: taking the maximum of two functions on the domain, or taking a function f and replacing it on some subdisk D in the domain by the harmonic function with the same boundary values. A set of functions on a domain U closed under these two operations is said to be a Perron class. Perron's theorem gives a method to construct a harmonic function from a Perron class. It says the following: let X be a Perron class on a domain U. Let's define a function f bar whose value at each point z in the domain is the supremum of the values of f of z over all the functions f in the Perron class X. Then the function f bar is either harmonic or identically equal to positive infinity. The property of being a harmonic function on a surface is preserved under a holomorphic change of coordinates. Likewise, the property of being a subharmonic function is preserved under a holomorphic change of coordinates. So we can talk about harmonic and subharmonic functions and apply the Perron method on an arbitrary Riemann surface. Let S twiddle be a simply connected Riemann surface and pick a point P in S twiddle. Let's choose a local holomorphic coordinate z defined on some open chart U containing the point P. Now let's construct a Perron class of suitable functions. Let's let X be the class of subharmonic functions on S twiddle minus P satisfying the following three properties. Firstly, we want f to be non-negative. Secondly, we want the support of f to be relatively compact in S twiddle. That means if you take the support of f and you add the point P, the result is a compact subset of S twiddle. Thirdly, we want the values of f near the point P to be controlled in a suitable way. We want f of z plus log of the absolute value of z to be bounded above near the point P. It is easy to construct subharmonic functions f with these three properties, so the class X is non-empty. Moreover, it is obvious that X is a Perron class, and therefore we can construct the function f bar by the Perron method. Perron's theorem guarantees one of two possibilities for the function f bar. It's either harmonic or it's identically equal to positive infinity. Let's suppose that f bar is harmonic on s twiddle minus the point p. The function f bar plus log of the absolute value of z is bounded near p. So the harmonic conjugate g of f bar is well defined near the point p up to multiples of 2 pi. And because s twiddle is simply connected, the function e to the power of minus f bar plus ig is well defined everywhere. Let's call this function phi. Now, since every function f in our Perron class X is non-negative, the same is true of f bar. Thus, phi maps s twiddle into the open unit disk D. In fact, one can show that it's a bijection, so that the uniformization theorem is proved in this case. The second possibility in Perron's theorem is that f bar is identically equal to positive infinity on s twiddle minus p. We pass to a subcase that s twiddle is non-compact. In this case, we can find an embedded proper ray gamma from r plus to s twiddle, starting at the point P. Let's define a family of Riemann surfaces, S twiddle sub T. The surface S twiddle sub T is obtained from S twiddle by removing part of the proper ray gamma, namely the part of gamma from T to infinity. Since S twiddle was simply connected, so is S twiddle sub T. Let's apply the Perron construction to S twiddle sub T to obtain a function ft bar for each T. The key point is that every function f in the Perron class extends continuously to 0 on the part of the ray that was removed, the part of gamma from T to infinity. Since that's true for every f in the class X, the same is true for ft bar. In particular, ft bar is not equal to positive infinity. So by the previous discussion, we actually obtain an isomorphism phi sub t from st twiddle to the open unit disk D. This is true for every t. If we find now a suitable scaled normalized limit of the phi sub t, we can arrange for them to converge, and what they converge to is a map phi from S twiddle to the entire complex plane. Case 2b is that S twiddle is compact. On the other hand, it's simply connected, so we know that it's homeomorphic to the two-sphere by the classification of surfaces. In particular, we can remove another point Q to obtain a simply connected non-compact surface, S twiddle minus Q. By case 2a, we know that S twiddle minus Q is isomorphic to the complex plane, and therefore, putting the point Q back, we deduce that S twiddle is isomorphic to the Riemann sphere. This concludes the proof of the uniformization theorem.